In the last class, our hero just entered and we have discussed what is his job. Think of cost function as the taste tester for machine learning models, but very much smarter. We could not have the proper introduction. Now let us introduce the cost function with the formal definition. In machine learning, a cost function is a mathematical parameter that measures how well a model predicts the relationship between the input and output data. There are many popular cost functions that are selected based on the problems. In this module, we concentrate only on the cost functions that are used in the regression problems. Let us try to understand them now. The simplest cost function recipe, the mean errors. Let's start simple. Imagine you have got y, the true value, the ultimate recipe you are aiming to prepare, and the y cap, the predicted value from your model, that is your chef's try. To evaluate, we compute the error y cap minus y. Then we find the average error across all data points. This gives us mean error cost function. J is equal to 1 by m, summation from I equal to 1 to m, y cap I minus yi. Here m is the total number of points. I hope this equation don't scare you. It looks horrible, but it is very sweet and kind from the heart. This line is our model. The points are actual data. For data point 1, for particular value of x, this is the value predicted by the model, and the point is the actual value of y. This difference between them is, say, delta 1. That is what we called y cap minus y in the equation. Similarly, we find delta at all points. So we used summation from I equal to 1 to m, number of points. That is mathematical way of saying y cap 1 minus y1 plus y cap 2 minus y2 and so on till m. We find the average of errors by dividing the sum by the number of points, 1 by m. This is what this equation says. This gives the mean error of all points. If error is least, a good model. If high, bad model. That's it. Sounds fair, right? Well, hold on. It's actually a terrible idea. Why? Because errors can be positive or negative, and they will cancel each other out like a pair of grumpy siblings. If we have this as the data, and this is a model, what is your observation? Data and models are opposite of each other. But delta 1 is equal to minus delta 6. Delta 2 is equal to minus delta 5. And delta 3 is equal to minus delta 4. When you add them, we get 0. According to mean errors, this is a perfect model. So you think your model is doing great, when it is actually messing up big time. It is the time to fix the flaw. We upgrade to the new cost function, mean absolute error, MAE. The idea? Forget the sign. Just take the absolute value of errors. J is equal to 1 by m, summation from I equal to 1 to m, absolute of y cap I minus yi. We ignore the sign of errors. No more positive or negative drama. It's all about the magnitude. This is like saying, hey, an error is an error. Whether you add salt instead of sugar or vice versa, it's still a messed up recipe. While this is better, it is not perfect. MAE treat all errors equally, which means a tiny slip-ups and a big disaster are weighed the same. That is not fair, isn't it? So the champion of the game is mean squared error, MSE. Now comes the champion. Here we square each error before averaging. So cost function j is equal to 1 by 2m, summation from I equal to 1 to m, y cap I minus yi squared. Why square the errors? Glad you have asked it. Reason number 1, it punishes big errors. Squaring amplifies large errors. A mistake of 5 becomes 25, while 0.5 stays 0.25. A big mess-up screams louder, forcing the model to pay attention. And reason number 2 is no negative errors. Squaring automatically handles the positive-negative issue. And that sneaky 1/2 in the formula, it is not just there for fun, it is for mathematical convenience. When we dive into the derivatives in the next spicy chapter, you will thank it for making life easier. So in summary, mean errors are a bad idea, like baking cookies without sugar. Mean absolute error, decent but not great. Mean squared error, MSE, the champion matrix that highlights big problems and make your model shine. We use MSE in our future models. We have armed ourselves with shiny new weapon, the cost function, the ultimate machine learning taste tester. But how does this weapon behave? What secret does it hold? Let's embark on an adventure to decode its mysteries, like the Sherlock Holmes of the data. Imagine a magical world where data is perfect. Hard truth is that it is possible only in imagination. Real-world data always have noise, errors, and that one feature that refuses to cooperate, like pineapple on pizza. That's okay. We assume we have a perfect data. Every prediction aligns with the truth, like a romantic movie plot. In such a case, your cost function j of w, b would be 0. 0. That's like getting flawless 10 on 10 on a dish from the master chef. Here is our small but perfect data. X is equal to 1, 2, 3, 4 and 5. Y is equal to 3.5, 5, 6.5, 8, 9.5. Plot this. Just by visual observation, we can say it is following a beautiful obedient straight line. We can join all these points with a straight line. Our aim is to find the equation of this perfect line. Find the perfect weight W and bias B of this model. Are you ready for this thrilling mystery solving? We have to solve two mysteries, W and B. Let's concentrate on W. For now, let's ignore B and let it chill at 0. Why? So we can give W our undivided attention. With B is equal to 0, our prediction becomes y cap is equal to Wx. And the cost function simplifies to j of W is equal to 1/2m summation I equal to 1 to m Wxi minus yi, as y cap is Wx. Now let us have some case studies. Playing with W. Let's test different values of W to see how it affects our cost function. Case 1, W equal to 0. J, that is function of W is 0 now, is equal to 1 divided by 2 times m. M is 5 data points. Irrespective of x, Wx is 0 as W is 0. So 0 minus y1 is 3.5 whole squared plus 0 minus y2 5 squared plus 0 minus y3 is 6.5 squared plus 0 minus y4 that is 8 squared plus 0 minus y5 that is 9.5 squared. Crunch the numbers. I get 23.375. J of 0 is massive. Our model is not so perfect, but that's okay. We are just starting out. Case 2. Now let's try W equal to 1. J of 1 is 1 divided by 2 times 5. Wx1, 1 into 1, that is 1 minus 3.5 squared, plus 1 into 2 minus 5 squared, 1 multiplied with 3, that is 3 minus 6.5 squared, plus 1 multiplied with 4, that is 4 minus 8 squared, plus 1 multiplied with 5, that is 5 minus 9.5 squared. Calculating it, we get 6.375. Very much better than previous, but still not great. The cost function is like, man, you are trying, but not hard enough. So let's have case 3, w equal to 2. J of 2 is equal to 1 divided by 2 times 5, wx. W is 2, 2 multiplied with 1, that is 2 minus 3.5 squared, plus 2 multiplied with 2, that is 4 minus 5 squared, plus 3 multiplied with 2, 6 minus 6.5 squared, plus 2 multiplied with 4, that is 8 minus 8 squared, plus 2 multiplied with 5, that is 10 minus 9.5 squared. We get 0.375. Look at that. Errors are shrinking. J of 2 is feeling optimistic. Case 4. W equal to 3. So J of 3 is equal to 1 by 2 times 5. 3 minus 3.5 squared plus 3 times 2 is 6 minus 5 squared plus 3 times 3 is 9 minus 6.5 squared plus 3 times 4 is 12 minus 8 squared plus 3 times 5 is 15 minus 9.5 squared. That is 5.975. Suddenly, J of 3 shoots up. Our model changed its path and start making wild predictions. Now to understand, let's analyze J of W curve. If we plot W versus J of W, we get a curve shaped like U, or more precisely a jar. As W increases, J of W decreases initially. At some magical value of W, J of W hits rock bottom, that is called minima, and then J of W increases again. The moral: the weight at the minima is the winner. That is the value of W that makes our cost function the happiest. Now expanding the plot by adding bias, B. Just working with the W to find the cost function J will mislead our calculation, because to be the perfect model, there must be equal contribution of bias. Now if we throw bias B into the mix, things get fancy. The cost function becomes 3D. We find the cost function for different combination of W and B, and the findings are plotted on the 3D plots, with W on x-axis, B on y-axis, and J on z-axis. What is our observation on the plot? A surface that looks like a funky bowl. Our mission: slide down to the bottom of this bowl and find the best combination of W and B to find the minima. It is the time for the entry of the navigator, the gradient descent. Finding the minima might sound like a treasure hunt. And guess what? We have a map. Gradient descent. This is the superstar algorithm that will help us navigate the bowl, dodge the pitfall, and land right at the bottom. And that's the tale for another lesson. Finding the best model is like fine-tuning a dish. With the right W and B, we can make our model taste just right. The cost function guides us, and gradient descent will lead us to victory. So grab your tools and get ready to dig deeper into the machine learning world. Here is the fact: the best is yet to come.